home, we can kind of briefly cover that one to kind of close out the chapter and make sure we understand all these concepts before the test, which is on Friday. So, yeah, test time. Woo! Woo! Y'all are excited for the test. That's surprising. Absolutely surprising.
Just get here whenever you can.
Well, I mean, they're on the wrong turn, and then we went on the down turn, and now we're here.
Alright, just go ahead and get out your study guides, and then we can go ahead and get started with all of this. So, who feels like they got all the questions right on the study guide? You guys got one on?
I never got like 3.
2, 3. Alright, anybody else feeling confident? No? Not feeling confident? Oh no. That's okay. We're gonna go through these, figure out what's been going on with some of these, and kind of go through them to figure out what we're missing on this. So, without any ado, we'll go ahead and get started then. So let's start with question 1. What are the 6 given prefixes for the metric system? So the ones that we gave you to make sure that y'all know. So we'll just go down one at a time, and y'all give me one of them. So, Olivia, give me a prefix that we're using. Deca. What is deca? Is that 10 to the what? What are we talking about with deca? 10? Just 10? Yeah, exactly. 10. Cooper, what do you got?
Kilo.
Kilo. How far is this?
1,000.
Thousands. Perfect. All right. Carson, what you got?
I said hecto,
Hecto.
which I realize now.
Yeah, it's not one of the ones that we gave you, but just to, you know, just since you've talked about hecto, what is it to?
Isn't it like 8 or?
No, it's a hecto. Hecto would be to the hundred, so it'd be right in between deca and kilo. But that's not one of the ones we gave you, so we'll keep going then. So Taylor, what do you got? Deci. Yep, that is one. Oh, you know what? I realized that we didn't give deca. Oops. So we'll have to go through this. I saw deca and I thought decky. So, but now you know that's to the 10th, and it's good that you know Cooper that's to the 10th. However, it's not one that's going to be on the test. So, deci. What is deci to? 10th place. There you go. So 0.1 or 0.1 if you want to make it look nicer. All right. Madison, what you got? Millie. Okay, Millie. What is that to? Thousandths place. Perfect. All right. So we'll go loop back around. Olivia, do you have another one for us? Centi. What is that to? Hundredths. Okay, I'm running out of room here. I probably should have written these further down because we have 2 more that are past milli. Anyways. Cooper, do you have one of those?
Micro.
Micro. And what is micro to?
10 to the negative 6.
Yep, 10 to the negative 6. I'm not going to write out 6 decimal places, but y'all get the point. And then the last one, what do we got for the last one? Carson, you got any idea? You don't. Taylor, Madison, you just raised your hand. What do you got? Nano. What is nano to? You gotta count it out. I get it.
Isn't it like 12?
Not 12.
9.
Okay, 9. There you go. So 12, I believe, is pico. So it's a bit further down. So that's past that, and we don't really get into pico with the AL chemistry. But further on in chemistry, a lot of the times you'll be working in pico. So just depending on the circumstance. But Yeah, nano is too big. Alright, cool. So let's go to the rest of these problems. Does that make sense to everybody? Remember these 6 prefixes. Those are the prefixes. Those are what they go out to. Any question on that? No? Perfect. Alright, let's go to these problems.
Be able to convert between
Yep.
all of those. Okay? And remember, just subtract your exponents. It tells you whether to move it left or right.
Alright, so let's start with this first one then. So we got 1 kilogram of baking soda. And I want to know how many centigrams would that be? So who thinks they've got that? This is part B on the first question.
Oh.
Centigrams from kilograms.
I would say 10.
Just 10? So kilograms to centigrams.
Oh, no.
Yeah, yeah. So that would be from kilograms to hectograms. So seems like you're on the verge. Madison, what you got?
Wait,
Never mind.
I got 100,000.
100,000. Yeah, there you go. That would be right. So it is 100,000, right? So remember, this is 10 to the third. If we talk about centigrams again, that's centimeters. For centigrams, we're at 10 to the negative second here. So we take our 1, 10 to the second, 10 to the first, 10 to the 0, 10 to the negative first, 10 to the negative second. Boom. Centigrams. Does that make sense? Awesome. So we'll do the other ones. So to nanograms, if we got it in 10 to the negative second here, what is it going to be in nanograms? You're adding a lot more, right? But how many? For nanograms?
Oh, nanograms would be
So you have it in one of our units, and actually I think you have the answer for D there with 4. But for nano, what are we moving into? What? 3 more zeros, right? Because nano is 10 to the 9th. I did that on purpose so y'all aren't, make sure y'all aren't sleeping on how we switch between those. Remembering that nano is 10 to the 9th and micro is 10 to the 6th. So, if we're going to do that, again, we have third, or 10 to the negative third, 10 to the negative fourth, 10 to the negative fifth, 10 to the negative sixth, 10 to the negative seventh, 10 to the negative eighth, 10 to the negative ninth. Now that is a lot of zeros, and I don't want to write those zeros out. So, how do we get this into scientific notation?
100 times 10 would be
So you move the decimal point, you're right, Taylor, as Cooper's doing the math on the decimal point, how many?
12.
12? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, exactly. So 1, 10 to the negative 4th. Or sorry, no, 10 to the 12th. Does that make sense? Cool. And then if we were going to talk about part D, we're in micrograms. We kind of, Cooper already spoiled that part. But again, it's going to be 1, 10 to the 9th. Now I suck at writing micro, but I think it's something like that. It's a weird symbol. So make sure to remember that. It's like the U kind of with a P. It's really weird. So if you see that on a test, know that's micro and that's the 10 to the 6th. It's just, I hate that that's there, but also we have milli already, so we kind of had to figure out something else for the other end. So here's what it is. Everybody see that? That makes sense? Cool. Perfect. We'll move on then. Plenty of study guide to go. Alright. Base SI units for length, mass, temperature, and time. So we'll start with length. Who's got me on that one? Olivia. Meter, yeah. Length per meter. Alright, how about for mass? Not just grams. Kilograms. Thank you, Carson. So yeah, technically the standard is kilograms. A lot of the times we end up just using grams, but if we're talking about the official standard, it's kilograms because that's what the measurement that they use in France somewhere to determine the weight of something or the mass of something. they use kilograms, but yeah.
So on the test, we should just focus on kilograms, not grams.
It depends on what the test asks you for. So if we're talking about just what the base SI unit is, yes, we need kilograms, because that's the base SI unit for mass. But if it wants you to put something in grams, or if it wants it in grams or milligrams or something like that, do the grams or milligrams. So just make sure to read the question and make sure to see what it's asking you for. Alright? Next two should probably be pretty easy here. Well, actually, the last one for sure. But temperature. What is base SI unit for temperature? Celsius is close, but not quite. There's another temperature that we use. What do we use there? Kelvin. There you go. Right. So Celsius is close to that. I mean, basically, it's what we it's just not the absolute version of it. So the absolute version is Kelvin, but you can convert from Celsius to Kelvin pretty easily. How do we do that?
Subtract 273.
Not subtract. If we're going from Celsius to Kelvin. Add. Yeah, there you go. Add 273. If you want to go from Kelvin to Celsius, yeah, you can subtract 273. But if you're going from Celsius to Kelvin, you're adding 273. All right. And then last one, SI unit for time. Seconds, exactly. There's not really any other units for time, really. So that one we're all familiar with. Okay? Makes sense? We got these four? Awesome, cool. Move on to the next question. Thomas, can you scroll down? All right. So we kind of went over this earlier. What is the difference between accuracy and precision? So I guess this would be a good time to, well, actually, I'll see if y'all can explain it first, and we can kind of go through the graph and see it from the graph from the other stuff. Yes, Taylor. Yeah, go for it.
Okay, so accuracy is like how close you are to the accepted value.
Okay, so
And then
precision. Yeah.
is how often you get the same answer.
Yeah. So I'll say it again for the online kids so they can hear. So accuracy, what Taylor said, accuracy is how close you are to the accepted value. Precision is how many times you get the same answer. So again, kind of from a few nights, or from when did I discuss that? Monday, Tuesday. So you can have something that's accurate but not precise, something that's precise but not accurate, etc., etc. Right? Okay, so now we're going to talk about the problems that I gave you right here. So given two sets of measurements, we've got 15.02, 15.25, 14.77, and then 14.8, 14.7, 14.8. If the known mass was found to be 15.0 grams, which set of data showed the greatest accuracy, number one or number two? One, right? Why?
Because it's closer to the actual value.
Exactly, and if you do especially if you do the averages between these two, you'll see that it's closer to the expected value there. Okay? So, which set shows the greatest precision?
2.
Two, why?
Because all results are all pretty close.
Yeah, because the results are all really close to each other, so the same measurements pretty much between these three. So when we go over the density worksheet, we can kind of see that a little bit more with the graph, and we'll be able to see kind of how that compared. But we'll go over that after we get through this. So, all right. Okay, cool. The problem's done. So, what do error and percent error measure? So, who wants to give me what error measure? Let me double check. Here we go. Yeah. So, who wants to give me error? What does error measure? Everybody have that one? What about percent error? What does that measure? Yeah, so it's a measurement of how far away you are from the actual value. So for error, I think we didn't really go over error as much as percent error on this, so I can go ahead and go over that. So generally the error of experiment is the absolute value of the difference between the experimental value and the actual value. So pretty much it's just reading the to define error, you're pretty much reading this top value here, because that's the error. So the error by itself is just the experimental value minus the actual value. And then if we're talking about the percent error, that's a better measure of how close we are to a value, because now we're taking the actual value and giving it a percentage so we can kind of see that better. So that's kind of the difference between the two. The error is just kind of what's on top. The percent error is how close it is because we're doing the percent calculations, if that makes any sense. Okay? So, with that being said, what was the percent error for the average of each of the data sets in problem 3? So we'll start with data set 1. What was the percent error on data set 1? Who's got me? Taylor.
For the 5, 15, or 2 is 0.13.
Sorry, what was that?
0.13.
0.13 you got for the
1502.
1502 set. Okay. So 0.13. And then for part 2, this data set 2, what'd you get? Anybody? Percent error for part 2. If you get negative number on the top, so remember the top is the absolute value. The negative number, if you get a negative number, it kind of represents that you were like below the expected value. So you can use negative numbers, but it just depends on how you want to format it. So if you got like negative something, that's fine. That just shows you how off you are from like under, if that makes any sense. So what'd you get? 1 point what?
33.
1.33? So let me make sure our sig figs are right here. So I got pretty close to what you got. Mine were a little bit off too, so that might be a rounding error, just calculation error. But yeah, that's about where we're looking. Does anybody have similar to this? Anything different? What'd you get, Madison?
I got 0.09 and then 1.56.
So you got 0.09. Because you're at this, and then you got so yeah, this is actually what I got. So that's what I got when I did this. So it might have been some kind of calculation error with you, but you got pretty close to these values. I mean, this is a little bit off, more off than this one, but these are pretty much the same because this is negative 1.3. So as long as it's like fairly close in between, like we're not going to count off too much there, really. So it's just making sure to double check your calculations to see if you got everything right there. Does it make sense? Any other values that y'all got? Do we need to go how to calculate percent error? Yes, we do need to go over that? No.
It's
Okay.
just the value you got minus the value you should have gotten. You have to divide that and divide it by the one you should have gotten.
Yep. Yeah, so it's the value that you got minus the value that you should have gotten over the value that you should have gotten times 100. And so you can do absolute value on the top just to make sure you don't get negative numbers. But the negative number just refers to how, like, it's how off you are if you're coming from below versus how off you are coming from above, if that makes any sense. I'm trying to explain it a different way, but but yeah, does that make sense for everybody how to calculate percent error? Because that's going to be important on the test, all right? Cool. So we'll go ahead and move on to number 5. Ms. Hobbs, can you scroll that up, please? Okay. So, what is the difference between qualitative and quantitative data? Carson, yeah, what do you got?
I said quantitative is numbers and qualitative is more descriptive.
Yeah, so qualitative is more just about describing, there's not really any numbers. Quantitative uses numbers to describe the data, essentially. Yeah, so that's exactly right. So we're going to do some examples. I've noticed that my solution turned blue once the chemical reaction started. What kind of data is that? Qualitative or quantitative? Qualitative, yeah, exactly. All right. I weighed 3 different samples of baking soda, and they came out to be 14.2, 13.9 grams, and 13.8 grams. What kind of data is that? Quantitative, yeah. Yeah, that one's Not too hard, it seems like all y'all got that one. Just the difference between, just remember the difference between qualitative and quantitative, so that's it on that one. All right, now we're gonna get into some scientific notation. So, for number 6, part A, 4.59 times 10 to the 9th. What number is that? Anybody want to just, actually it's probably easier if y'all just like came up and wrote this on the board, so who wants to give it a crack? Give it a shot.
Number 6.
For number 6, part A. You think about it? Alright?
I don't know what that is.
Go ahead and put it on the board, we'll see, alright? There you go, feel free to use that. If I can find another marker to use. Yep.
There's a freeze button.
Oh, gotcha.
So, was I supposed to put it in the full number or was it?
Yeah, the full number, because that, I wanted to figure out what number. So, 4.59 times 10 to the 9th. So, okay, so you said take off 2 zeros, right? Alright, so, the reason that is because, again, remember we're counting decimal points here, right? So, if we were to go back from this number, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that would actually be 4.59 times 10 to the 11th. So remember that this 9 is not talking about the number of zeros, it's talking about number of movements of the decimal point. Remember. I want to stress that a lot because a lot of people think that's 0 and I think that's like the biggest like mistake that a lot of people make on this scientific notation. Just remember it's movements of decimal place here. So generally when you have numbers that are bigger like this one, it's going to be like the number of zeros minus 2 because that's just how many times you move the decimal place on that one. Does that make sense? Alright. So with that in mind, who wants to try part B here? So I want negative 0.000. Zeros I put on there. 6. There we go. 3, 2, 8. In scientific notation. Who wants to try that one? Alright, Madison, go ahead and try it. Just write it. Yeah. You can do the work if you'd like to, just to show it, but if you, I just need the number to see if you got it. Alright, 3.28 times 10 to the negative second. Do we agree?
I
Or
put a
7.
negative before the 3.28.
Yeah, so Carson said you put a negative right here. So what do we think? Do you think that this number is going to be positive or negative?
Negative.
Negative, right? Because again, this doesn't matter for this chain. When we talk about negatives in the exponent here, that's again showing you how many times you move over the decimal place. So if it's negative, you're moving it towards the left here. If it's positive, you're going to be moving it towards the right. Alright? So the negative sign in front doesn't really matter too much, but still good job on getting the right scientific notation on that one.
So you remember put the negative sign in front and the negative?
So I mean, like it was a negative number, so that's why it ended up being a negative scientific notation. The negative in the exponent here is just the movement of the decimal place. It doesn't matter whether the number is positive or negative. It's just like how big or how small. So generally with the negative 7, that means you're moving it towards the you're moving the decimal place towards the left in order to get it to scientific notation, or sorry, to the right. So like I would be moving it this way if it was negative, right? But if it's positive, you've got a number that's like, ignore that that's a z and not a real number, but you're moving these to the left, right? And that's if it's positive. Does that make sense? So
So
that is.
positive exponent is greater than 1, negative exponent
Yeah.
is less than 1. Yes.
So yeah, so that, and that's why that doesn't really matter for the negative. So like if this was negative 272, I guess that's the 2 that I wrote. I don't know, I wrote the number, so. So So this would be like 1, 2, 3, 4, 5, 6, 7. So negative 2.72 times 10 to the positive 7. Alright? Cool.
But, for this problem, like, that person said we did, like, she said, the negative times the 3.
Yeah, you lose the negative because it's still a negative number. Right? So that doesn't, so this negative place doesn't tell you how many times you're supposed to move the decimal over. It just tells you whether the number is a positive or a negative number. This is like, so that doesn't really have an effect in the exponent here. So you still want to move it to the front here because that's still the number. It's just that this is saying that this is a really, really big negative number. And this is saying that it's like a really, really tiny positive number. Make sense? Alright, so we'll go to the last problem there. Do a little math on this one. So part C, I don't know if anybody come up here and do it. We just need the answer for this one. So I need, scroll down so to make sure, because I did the calculation beforehand, so I didn't have to do them live and take up time. So what is 3.4 times 10 to the negative 4th divided by 6.9 times 10 to the 10th? Who has an answer for me? Any guesses? No one? Nobody figured it out?
Does everybody know how to put scientific notation into your calculator?
Question 6.
Yes, instruction 6 part C.
Oh, okay.
That didn't make any sense.
It said it didn't make sense?
Yeah, when I put it in the scientific notation. So then I tried to calculate it like normally, but I still think I got it wrong.
Gotcha. So we'll go ahead and practice this one and put it in scientific notation. So again, what you're going to want to type in your calculator. Actually, it depends on your calculator. Some calculators have a mode and some don't. So to avoid something messing up, if you don't have like anything, you just have like parentheses in your calculator, you can always type it in, like parentheses, what did I put down number-wise? I could put 3.4 times 10 exponent negative 4, and then I could just close parentheses, divide it by 6.9 times 10 exponent to the 10, close parentheses, and do it like that. Some of you have like exponent buttons, and I think that's like, it's like, sometimes it's like an undercase E, but that can also be, so I think what, some of the calculators write scientific notation as E, but this is also a number used in some places. It's like 2.7 something. So if you type E and you got a really weird answer, that's probably what that E on your calculator is referring to. So if you got a weird answer from E and it doesn't really make too much sense, I would just not even use it and just go with this method. It takes a little bit longer, but it's going to like surefire guarantee that you put in your scientific notation. So if you're looking for the exponent button and you can't find it, I would go with that. Just because you basically just write it out and you waste 5 seconds for guaranteed accuracy, essentially. So go ahead and put this in your calculator and tell me what you get. Or if you know how to do the exponent button in your calculator, you can do that. Or the scientific notation button in your calculator. So I can't really, unfortunately, I don't know which calculators y'all have, so I can't really say what button you should be pressing there. But this works on every calculator that has those functions.
Use the suffix first?
Yeah, make sure you suffix. 5.8 times what? Times 10 to the negative 15, right? Yeah. You got pretty close to the right answer. I have 4.9 times 10 to the negative 15, but you got like 5.8. So again, it seems like a lot because it's like, whoa, one whole number. But remember, it's 10 to the negative 15th, so this is like 0.000000000, and then you were off by 1 digit. So it is fairly close. So what I got is this. But Taylor, you got like 5.8. Which one? Good job on using proper sig figs. That is correct. Because we have 2 sig figs here, 2 sig figs here, 2 sig figs. So, good on that. Everybody get similar answers?
Let me see a copy.
You might have typed it in, maybe you missed or a number or two there on that one, but you get similar numbers around this area? Yeah? Yep. Okay, cool. So that's just a kind of a base way to put these kind of calculations in your calculator. Just put parentheses around them and then do your calculations. It'll make your life a little bit easier if you can't find the right number or the button.
6.7.
Oh, see, yeah, that makes sense. It is more than likely you put it wrong. Okay. So we'll go ahead and move on. Alright, and scroll up.
Okay, you're gonna have to, unfreeze. There's a button on that thing that says freeze on it. at the
Oh,
bottom,
yeah.
Okay?
Okay, I didn't know that was a thing. Cool.
Is that where we are? No, that's-
Yeah, go down to 7. So I'll freeze it. There we go. Okay. Number of sig figs in numbers. So A, how many sig figs? You got 1. Okay, cool, awesome, good job. For B, how many sig figs? Yeah, just hold up fingers, right? 3, perfect, yep. Number 3, how many sig figs? 4, C4, 4, okay. Looks like we got that one, good job. No, and then D, how many sig figs? I see a 2, I see 2s, I see a 4, I see 2 4s and 2 2s. That, you change yours to 2. Alright, so we'll talk about this one. So the right answer is 2. Why is it 2?
Those aren't trailing
Leading
zeros.
Well,
So-
they're leading zeros, so they wouldn't count as,
Exactly. They're leading zeros, so they don't count towards sig figs. These leading zeros never, ever count. Your justification is right, but like just saying trailing zeros is easier than just saying that those aren't, leading or. I mean, sorry. These are leading zeros, not trailing zeros. You get what I'm saying. But you have the right answer still, so you understand the concept. Does that make sense? Got it? Cool. Do I have any more on here? E, yeah, okay, that math question. So 4.9 times 7.00, what do we get?
I don't think I know that, but 34.3.
34.3.
34.
So I hear a 34.3 and I hear a 34. Who agrees to 34.3?
I thought it was because 4.9, so I was like, it has to be in another distance.
See, so you're thinking about the math rules, right? And that's towards, so with addition and subtraction, you base it on least accurate measure. But for multiplication and division, correct answer is 34 here because you base it on what?
Not sig figs.
Number of sig figs, right? Exactly. So if we look at these two, 4.9 has how many sig figs? 2. 7.00 has how many? 3. 7.00. 0.00.
oh.
Yeah. Not just 700, 7.00. So you have 2 sig figs in your final answer. Alright? Make sense? Alright, so now the math rules. What is 34 plus 27.5? What do we get?
62 if you will.
Yep, 62, exactly. 62 because again, least accurate measure is to the ones placed here, you get to 62. Alright? Go on to number 8 and 9, so I'll unfreeze it, and there. There, again. Okay, so define density. What is density?
How very fast the molecule run an object.
True. What's the, how do you get density?
Oh, so mass divided volume.
Yeah, mass divided by volume. So you're correct on that definition. Yeah, density is how tightly packed out or in an object. But remember, density is just mass divided by volume. So both are correct. But it's good to remember that. Or I guess that was the right answer for D. Yeah. So it describes the ratio between the amount of matter a substance has per its volume. So you can use that. You can use just how densely, or how many. What did you say again, Cooper?
How how you pack the molecules are.
How tightly packed the molecules are, all of those are density. So if we're talking about units for density for solids and liquids, so for solids, what do we have?
Grams over centimeters
Grams over centimeters
cubed.
cubed. Liquids, what do we normally use? Kilo- Kilograms over liters? Is that what you said? What did you say?
I said grams over milliliters.
Grams over milliliters, that works too. That's a horrible you. And then what about for density of a gas?
Grams and
Yeah, grams over liters. Just because gas is bigger, so generally you can't really it's harder to capture gas in milliliters than some of those people just use liters. And that's just the common for this. Okay, number 9. So I have a mass of 4.56 grams. And my volume is 3.33 centimeters cubed. So what is the density? Who can give me that? Olivia, what did you get for density?
Oh,
1.37? And what are the units? You don't know the units? So remember, what did you do here? You divided this number by this number, right?
Oh, grams over centimeters.
Yeah, there you go. Always keep track of your units here. It's very, very important because you never want to forget what units you're working with because then you won't, you'll be confused. Like let's say you lose track and you're just like, oh, I forgot what unit. I guess I'll say kilograms per centimeter. That's way denser than grams per centimeter cubed. You're going to have completely different objects. So keep that in mind. Yeah, I think I got 1.37 too. Let me double check. Yep. So now we do a little bit of something different with this. Mass of the substance in question, 10.5 kilograms. How many liters is the liquid in question? Oh, I forgot the density. Density is 127 kilograms per liter. Alright, my mass is 10.5 kilograms. What's my volume? Who got it? Gotta do the math.
12.1.
You said 12.1 liters?
That's
You got 0.08? Yeah, so that's close to what we're looking at, 0.08. So what you probably did is you kind of solved for it like you were solving for mass here. But yeah, so for this one you have 3 sig figs, so you want to make sure you have 3 sig figs. So for what I got 0.0827. And 3 sig figs, 3 sig figs, 3 sig
Oh,
figs.
we did 10.5 combined.
Oh, sorry, what was that?
How did you put that into?
Yeah, we'll go through it real quick. It's a little bit of you. So remember, and this goes back to a little bit of algebra here. So we know that density is equal to mass over volume. So what we do first is just plug in our numbers. So we know density is 127 grams or kilograms per liter. I almost lost track of the units. I lost in the sauce. Very unfortunate. Then we have our mass, 10.5 kilograms. And we have our volume. So the best way to get the volume here is we want to kind of give volumes on its own. So first, we want to get volume on the top. How do we do that? Multiply by V, right? So if we multiply both sides by V, we get 127V. Remember this is kilograms per liter. It's equal to 10.5. Then we want to get V by itself. So what do we do with V? Or what do we do?
Divided by 127.
Yeah, divide by 127, you get V is equal to 0.0827. That make sense?
So is it, mass divided by density?
So what I did, yeah, essentially, it's mass divided by density in a sense, because that's what we ended up doing. So you can think of it that way, but it just depends of how you do the processing. So I would always start with just writing out the equation and plugging and seeing what you need and then figuring out what you need to do from there. So, yeah. Because basically you just flip that. So I know some people will also get it to where they can get to it being 1 over v, so they'll do like the dividing first. And then if you have like whatever number you have here, and you want to get this back on top, you just like do the inverse of this one. So you would just divide this by 1, and then divide this by 1, and you will get the over 1. So you basically just flip them. So there's different ways to do this, but you always want to start with the density equals mass over volume, and then go plug and chug, and then do what method feels the best for you, essentially. As long as it gets you to volume right. Does that make sense? Okay. We'll go on to number 10. What time is
Just
it?
wanna pay attention to, time.
Yeah, 1:37, so we only have a couple minutes left, so we're gonna try to go through this quickly. So we have this graph here. It shows time it takes for a certain substance to heat up. What variable is the independent variable, which variable is the dependent variable?
Time is the independent, temperature is the dependent.
Yeah, exactly. Time is independent. I mean, you could choose which times you're using, but this is just kind of doing its own thing. It's on the bottom right. Temperature is the dependent variable. Again, it's on the top. So, yeah, good job. All right, move on to number 11 here. Right at the end here, if you close there. So, direct proportion and indirect proportion. So, what happens with one variable when the other goes up in a direct proportion? Where does that one go, up or down? Up, direct proportion, they are the same. What about indirect variable?
The other ones.
Down, exactly. Perfect. That one's pretty quick to go through. Number 12. This is a unit conversion problem. Density of a certain object is 2.50 slugs per inches cubed. What is the density of this object in kilograms per milliliter? Did y'all attempt to solve this, try to figure it out?
I kind of attempted it, but I don't.
I did.
Attempted it, but you don't know? Alright, so tell me what you got then.
598.
I got .72.
Oh,
2.33 is what I got. So you got that right, Madison? So 2.23. Yeah, 2.23. Again, try to go through your numbers, see what you did wrong here. Essentially, again, when we're doing these density, these unit conversion calculations, try to set it up like this. It makes your life a whole lot easier. So basically, you want to get to kilograms per liter. So I like to do, you want to convert from kilograms. So in order to get rid of the slug to get to kilograms, you do your conversion right there. So slug X kilograms. I'm not going to do the whole calculation, but just show you what I'm doing here. So essentially you want to go from there, right? Now the important thing here is, and the one that probably a lot of y'all missed here, so I have 1 inch equals 2.54 centimeters. But 1 inch cubed does not equal 2.54 centimeters cubed, right? So if you're cubing your inches here, you gotta cube your centimeters too. So, and that's what you're gonna get your actual conversions. So try to keep that in mind. Same with squares, same with to the 4th power. If you're gonna be cubing your initial unit, and you're gonna get cube units here, you gotta cube what you're converting into. Okay? So with that in mind, try it again, try to see if you can solve it at some point. We're gonna go ahead and move on to the rest of this, just so we can make sure we get through this in time. So, number 13. So the graph, scroll down a little bit. So, and I can talk about the problem from my seat, and y'all should have it here. So, so we got a black line and a purple line. What was the slope of the black line?
2.9.
What'd you get?
Not the right answer. 2.9 inches.
2.9 now. It's
I got the, like the over or like the.
just the bottom one here. So,
Oh, I'm not sure which one.
bottom one here.
I
The bottom is black,
I
right?
said
Yeah.
five.
You said 5?
Yeah.
So this goes up by 20s, right? So if we have
Oh wait, it's 13.
20 and 2, and 4 and 40, and we do the slope,
I did 1.5 over 3.
40 minus 20, it is 5. Okay, so I actually put it in wrong, so it is 5. So that's on me, that's my mistake. Because yeah, you get 40 minus 20, you get 20.
I've got two.
No, I am right. Okay, cool. So 40 and 4 right here, 20 and 2 right here, rise over run. You do the math, so 0.2 minus 0.1, what does it lie? 0.2 minus 0.1. 20 over 2, 10. That make sense? Y'all think you can do the other one like this? I'll go ahead and spoil it for you. I want to make sure that y'all know this. So again, for part B, for the other slope for substance 2, it's going to be 30. And remember that the units on these are going to be grams per milliliter. Yeah. All right, and then so regardless, if we got this mass over volume graph, what do the slopes represent?
Slope.
What do they represent? If we've got mass over volume, density, right? Mass over volume. You're already calculating that, anyways. That's the unit for density. You gotta relate the two there. And then the last one here. So measurements for both the crayon and the pencil. So crayon, what do we get?
2.9
2.9 what?
inches.
Inches, yep, exactly right there. Again, we're measuring 2. So we're measuring by 0.25, but we're really kind of measuring by ones here. So we can kind of estimate to the tenths place here. If these were like by tenths, then we could estimate that, but since it's like by quarters, it's really weird. So 2.8, 2.9.
Pencil's a much better example.
Yeah, 2.8, 2.9 is about right. This one,
16.0 centimeters.
16.0 centimeters. Yeah, I'll take that. Anybody get like,
15.95.
That's what I was
yeah, 15 point what?
95.
So again, we're measuring by ones here, right? So how far can we go? To the tenths place, right? So instead of 15.95, what do we have?
15.9.
So that's if you didn't round up to
My bad.
16,
Yeah.
right?
Yeah.
Because you gotta remember that 0.5 goes into, and you carry the 1 over.
Because you know that it's between 15 and 16, and you can't break that up into 95
Yeah.
100s and be confident. The best you can do is say 9 out of 10.
Yeah. And like, and for this one, we would take anything like from 15.8 to 16.1 because again, it's very unclear. So that's where that point of uncertainty comes in. You're not really sure, so you can kind of guess around that. All right, does that make sense of how we do these? Any other questions on the study guide? No? All right, so
Okay,
we are,
go back to this one right here then,
yeah.
okay?
Yes,
So
sir.
for the pink line, what would be the mass of 100, let's just say, what would be the volume of 100 grams on the pink line? 100 grams would be at what volume?
33.4.
Well, it's right here, right?
3.4.
You come down, so it's gonna be, that's 3.5, so it's about 3.4, 3.3, right? So you can get the volume of any mass or the mass of any volume now off that graph. You know, does everybody understand how to read that graph?
Yes, sir.
So if I have two milliliters of let's go to 2.5 milliliters of the pink stuff, I come up here, well, I know it's gonna be, it's gonna be a little bit more than half, so it's 70, it's between 70 and 80. You just guess me. Okay, you are gonna have to be able to interpret graphs.
Miss Cunningham, come to the front desk, please.
So what happened there is that you probably didn't turn in the post-lab questions. Yeah, so the post-lab questions were the meat of that lab. The charts and stuff gave you the 10 points, but you didn't turn the post-lab questions.
Did I get late credit for it?
You get late credit for it. Do you have the questions on your person right now?
No, I don't.
Have you done?
He hasn't done it.
You didn't do them at all?
I think so.
Yeah, I'm sorry.
Yeah, done, it just didn't turn it in or whatever.
Yeah.
Darius Cunningham, come to the front desk, please.
And I tried to get rid of the lines.
You keep sending me emails.
I updated them, I sent you the link, but you're
Yeah.
gonna have to move my bonus up to where you want it. And change the point value.
Tanner Clifton, please come to the front desk. Tanner Clifton.
I don't know how you do this without whiteboard cleaner and not chuck an eraser to get all these lines off. I do the best I can.
That's the bonus. There. Right, so that one needs.
Yeah, I like the math.
So,
no
now,
blazers.
um,
It's not blazer. It's close though. I mean, you could.
Basically.
I'll suspend my belief and think it's blazers.
this one.
What? Is it dinosaur? It's close enough.
That's a place that tiger.
What is it? Dinosaur. For thee, raise up the banner for blazer victory.
You go, you go. Oh, come back. I didn't know that.
I'm a front year.
Nice.
I guess the other class knows more because I told the other class I was like,
4 hours ago.
I don't think I know.
Wasn't it? That's it.
Okay.
Or maybe you did, I just wasn't here when you were here
True.
the first like 2 weeks, so.
Very true.
Oh,
I'm sure this is.
Oh yeah, we need to stop.
let's keep going, should I stop it?